just a couple of results to look at. The first one's this. If we know a polynomial has k distinct zeros, then we can conclude that this must be a factor. We said x minus a1 is a factor, but then we're also going to say x minus a2 is a factor and x minus a3 is a factor. Well, therefore, all those things multiplied together must also be a factor, I guess is what we're saying there. If I want to show that 1 and negative 2, all right, factor theorem, sub in, yes, polynomial 1, that works out to be 0. Polynomial negative 2 is also equal to 0. As they're both zeros, we know x minus 1, x plus 2 is a factor. I can now find the other factor. What I've done to make life easier for myself is I've expanded out those two factors. It's a little bit easier to look at it and go, well, leading term times leading term, we must get x squared. Constant times constant, we must have plus 5. Now, well, I could pick any of the other three to work out the missing term. Let's look at the x's. At this stage, I have 5x. Oh, and that's what I want. So it looks like the other factor is just x squared plus 5. So there it is, completely factorised. X minus 1, x plus 2, x squared plus 5. Now, we'll take that a step further. If the polynomial has degree n, and we know n distinct zeros, then actually we know the polynomial. It'll be x minus a1, x minus a2, x minus a3, and so on up to x minus an. I suppose technically any multiple of that would also be an answer as well. So maybe we need a constant out of the front of that to have a complete solution. And the next thing, a polynomial of degree n cannot have more than n distinct zeros. Because if it did, then we'd have more than n factors, and then that leading term would then be higher than x to the power of n. So that's just not possible. We're going to write down, well, when we say a possible polynomial, we're sort of generalising it to cover every possibility. What we know is it has a double zero at negative 7 and a single zero at 2. So I certainly know that they are factors. But if I want to generalise this to cover every possibility, what I would need to say is, well, I could also multiply it by some other polynomial. But that polynomial can't have a 0 at 2 or negative 7. Because say it did have one at 2, then x minus 2 wouldn't be a single zero anymore, it now would become a double zero. And similar with the negative 7, if it had one at negative 7, it wouldn't be a double zero, it now would become a triple zero. It could be multiplied by some constant, although in this case do I really need to, because I am saying it's being multiplied by a polynomial and that constant could be in that polynomial. See, it doesn't hurt to have it, but you don't really need it, I suppose, for this one. If it was a monic polynomial of degree 3, in that case, I'll stop there. I know it can't have any more zeros because I've got 3 already. It's monic, so the coefficient of x cubed is 1, so there's nothing more I can do with that one. There is only one possible polynomial. If it was a monic polynomial of degree 4, again, I know I've got those two factors, but it's of degree 4, so it could be multiplied by some other linear factor, but a could not be 2 and it could not be negative 7. Again, it would change the nature of those roots. How about a polynomial of degree 5? Again, I know those two things are factors. I'm going to multiply it by a quadratic, but rather than say quadratic, I'm just going to call it a polynomial of degree 2, rather than write, I suppose I could have written ax squared plus bx plus c. It's easier just to say qx, which is of order 2. And again, it can't have a 0 at 2 or negative 7. Also, do I need the k there? You probably don't, because it could be in that qx that I set up. This one here then, which sort of looks like I'm contradicting myself, because previously I said a polynomial of degree n cannot have more than n zeros. And now I'm saying, well, what if it does? Hang on, you just said it couldn't. A polynomial of degree n, if it has more than n zeros, then we must be talking about the zero polynomial, which means basically that it doesn't matter what number you substitute in, you're going to get the answer 0. If you've got two polynomials, and you'll notice I've used the congruent symbol there rather than the equals symbol. See, if it was an equals symbol, we'd be saying, for which x values are these equal? You put the congruent symbol there, we're now saying, hang on, they're always equal no matter what value of x you put in. So they're equivalent, identically equal, congruent, they're all terms that mean the same thing. But what that therefore means is if they are the same polynomial, then all their coefficients must be the same as well. Now if I had something like that, what I can conclude is then that, well, A1 must equal A2, B1 must equal B2, C1 must equal C2, and so on and so on and so on for all of the coefficients. Okay, that is 10.